All right, guys, this is the review session for two variable data analysis. So in the last two videos, we were looking at one variable data. So basically sets of data that was only recording information on one variable. And we were looking at all the different graphical displays like histograms, dot plots, stem and leaf plots, box plots, and different calculations that you can do when you're dealing with one variable data. Now we're going to move over to two variable data. So the main graphical display that we're going to be looking at in two variable data is going to be a scatter plot, which is the image that I have on the right side of the screen here. And scatter plots are made up of paired data, right? So each data point on this scatter plot gives you two pieces of information on two variables. That's why it's called two variable analysis, or sometimes they'll call this bivariate data, right? So I'll just write bivariate across the top there. The prefix bi is for two, okay? And the idea here is to see if we can use linear models to find patterns in two variable data. So in this case, the two variables that are going to be compared here are the number of hours you spend studying versus your score on an exam, okay? Um, and you can see here that this looks like a pretty linear pattern. It looks like I could draw a line in here, and that line might be a pretty good model for this pattern. So maybe I would do something like that, right? I'm trying to create a line that minimizes the distance between all these data points and the line itself, right? This line you'll see called several things, right? You might see it called the line of, let me try a little better here, the line of best fit, right? That's one name for it. Or you might see it called the least squares regression line, right? And the reason that they call it that is because we're not actually trying to minimize the absolute value of the distance between these data points in the line. We're trying to minimize the squared distance between these data points and the line. So that's why it's called the least squares regression line. And what we can do with the least squares regression line is we can take inputs for what we call the explanatory variable. So that would be the variable down here on the x-axis, right? We would call this explanatory. And we can use it to make predictions about the response variable, right? So the response variable is what's going to be on the y-axis, okay? Sorry for my sloppy handwriting. I'm doing the best I can with the technology, right? But basically, we can now use, if we have an equation for the least squares regression line, all right, that models this data, we can use inputs from the explanatory variable, or in other words, the number of hours that we've studied, and we could use them to predict what somebody's score on the exam might be. And we can do this with all kinds of different two variable data and two variable relationships. Okay. Now, this particular scatter plot here would have a positive association between the x variable and the y variable. And a positive association is when values that are higher in one variable are associated with values that are higher in the other variable. So essentially, as your x variable or your explanatory variable increases, your response variable tends to increase. It's not a perfect relationship, but if you look at the general trend in these little X marks here for the bivariate data, you're going to see that generally the students who were studying more, basically those students who are further to the right on the x-axis, also tend to be higher up on the y-axis, right? So we can look at a quick practice question before we get into the rest of the lesson here, right? So they give us a question and they give us basically 3 statements, and we're basically asked to choose which of these 3 statements has to be correct, right? Or if there's more than one of these statements that are correct. So statement 1 says a line might fit this data well. And I would agree with that, right? I can probably draw a line in here that does a pretty good job of modeling this pattern, right? This line looks like it fits this pattern well. So I would say that this is a linear pattern. And I would say that statement 1 is true. Statement 2 says the variables are positively associated. Now remember, like I said in the last slide, and let me try and clean some of this this writing up here, but you know, positively associated variables mean that you're going to see an upward sloping pattern, right? As one variable increases, the other variable tends to increase. That's not what I see here. What I see here is a negative association, meaning as my x variable is getting bigger, it looks like my y values tend to be decreasing. And that's called a negative association, not a positive association. And you can think back to algebra when you think about not negative and positive slopes, right? So I would say this is definitely not a positive association, right? And then we look down here at choice 3, the variables are negatively associated. We just covered that. So this one would definitely be E, 1, and 3 only. Okay. So we have positive association, we have negative association, and then if you had a scatter plot, and I'll show you some in a minute, but if you had a scatter plot where you couldn't make any kind of sense out of the pattern, you can't pull an upward sloping pattern or a downward sloping pattern out of the picture, then you would say that these variables are not correlated in any way, okay? Or that they don't have any type of association. That doesn't mean there's not a relationship between the two variables. It just means they're not correlated in any type of way. We can't pick up a pattern. As the x values increase, it doesn't really help us determine what's going to happen on the y-axis. Okay, so then we get into correlation, which is how we measure associations between these two variables, the bivariate data that we're working with, right? We can measure the strength of the relationship between the two variables. And we use the letter R to represent correlation, or the correlation coefficient. Okay, and you can see here that this thing has a pretty wild formula, right? You would have to sum all the individual observations, their x coordinates minus the average x value divided by the standard deviation of the x variable times all the individual y values minus the y average divided by the standard deviation of the y variable, and then multiply that by 1 over n minus 1. We did not cover this formula extensively in class, and that is because of the text right down here where it says, fortunately, the formula for the correlation coefficient is given to you on the formula sheet, and there is almost no chance that you'll actually need to use this formula. That's right out of 5 steps to a 5, and that's why I didn't spend a ton of class time talking about this formula this year. There are some formulas in this chapter that you do need to know, and I'll show you where they are on the formula sheet in just a little bit, and I'll show you how to use them. But calculating correlation itself is not really something that I don't think they're going to ask you to do on the exam, and that's verified in the 5 Steps to a 5 book, right? So we're talking about R, and I have some properties of R on the next slide, and we'll talk about that in a bit. But just so you know, we're all clear here, R is always measured between -1 and +1. All right. It can only take on values between -1 and +1. Now, a correlation of +1 is a perfectly upward sloping line, right? This would be R equals +1. It means the x variable can perfectly explain the y variable. There is a constant rate of change for every 1 unit increase in the X variable, you are going to have some constant corresponding unit increase in the Y variable. And that would be a perfect correlation or a perfect relationship. All right. And then if you had a perfectly downward sloping line, right? The slope doesn't matter here. If it's sloping down and it's in a perfect straight line, you're going to have a correlation of -1. And it's the same thing as a perfect positive relationship, except in reverse, right? As the X values are increasing or as we move to the right, the Y values tend to be decreasing. And that relationship is perfect, meaning every 1 unit increase in the X variable is going to lead to some constant decrease in the Y variable. Okay. And then over here on this chart, right, if we're not going to look at perfect relationships, right, many correlations are not perfect, right? There aren't too many variables that occur randomly in nature that are perfectly associated with one another, at least not the ones that we're going to study. We're generally going to study the variables that have correlations somewhere between -1 and +1. And you can basically see that the tighter the dots are grouped together, right, the higher the correlation is. So this is an upward sloping pattern. It's pretty tightly grouped. And so you have a correlation of positive 0.8. Okay. Here's a weaker positive correlation. I would say this correlation is probably moderate. So maybe I shouldn't use the term weak. It's still upward sloping, right? But the dots are a little less tightly packed together, and so the correlation's not quite as strong. It's only 0.5, right? Remember, a perfect linear relationship is 1. So 0.5, it's moderately strong, all right? And then here's a weak positive association, a correlation of plus 0.3. I can draw lines of best fit through all these data points, and you can see the upward sloping pattern is apparent, okay? But as we move from the left image to the right image here, you can see the pattern getting weaker and weaker, okay? Underneath is some examples of your negative correlations. They're of the same strengths as the ones in the top row, but they're just moving in the negative direction now, right? So this is a pretty strong downward sloping pattern. So the correlation is -0.8. All right, this middle one has a correlation of -0.5, and the last one has a correlation of -0.3, right? So you can see the relationship is getting a little bit weaker as I move from left to right. And then the last one down here shows you that these two variables are not correlated in any way at all, right? I really can't associate an upward sloping pattern, right? Is this an upward sloping pattern? Is it a downward sloping pattern? It's really hard to tell, right? So correlations close to 0, you're really going to see random scatter, okay? And you're not really going to be able to make sense of the pattern you see. And that kind of makes sense. A correlation of 0 basically tells you that knowing the X variable is not going to help you predict the Y variable at all. That's not true for these other two rows, right? In the top row, for something like, a correlation of plus 0.8, right? If I know I have a very high value of X, I can probably predict that my Y value is also going to be pretty high. And likewise, if we look one graph below, with a negative correlation of 0.8, you can see, right, if I have a very high value of X, we can probably predict that that's going to be associated with a very low value in Y, okay? But when the correlation is 0, if I just box in part of this chart here, I would say everything in this rectangle that I have drawn for you, right, it has a high X value, right? It's all the way to the right on the chart. But if you look at the Y values, they're all over the place. There's a couple high Y values, there's a couple moderate Y values, and there's a really low Y value. So if you look at this graph, it seems like knowing where you are on the X-axis does not really help you predict what's going on the Y-axis. And so that represents a correlation of 0. Okay? So there are a couple really important things, right, that we should know about correlation, right? If R is above 0, it means the variables are positively associated. If R is below 0, it means the variables are negatively associated. In other words, if R is bigger than 0, you're going to see an upward sloping pattern. If R is less than 0, you're going to see a downward sloping pattern. Okay? The second bullet point here, if R equals 0, it indicates that there is no linear association that would allow us to predict Y from X. Now, this is important. It does not mean that there is no relationship between the variables. It just means that relationship is not a linear one. Okay? It does not matter which variable you call X and which variable you call Y. R will be the same. In other words, R depends only on the data points themselves and not the order of the XY pairs. So what do I mean by that? Right? If I had a graph and I said we were trying to predict height from weight, right? And I had an upward sloping pattern, maybe like this, right? It doesn't matter if I switch the axes. I could put height on the y-axis and I could put weight on the x-axis, and I could try and predict people's heights based on their weights. All right. This pattern, the slope might not be as steep. If I switched the x and the y variable, I might get a more moderate slope, right? But the correlation remains the same. In other words, the relationship between the two variables doesn't change if I switch which axis I plot them on. So that's important to remember. This one's important to remember right here. And then the last two bullet points, R does not depend on units measured, right? That's kind of intuitive too, right? Like if you think the example they give here is if I change from measuring hours studied to minutes studied, the correlation shouldn't change. And that should make sense. If I come back to this first scatter plot, right? If I converted everybody's hours studied into minutes, right? This graph shouldn't really look different, and the relationship's still going to be the same. It doesn't matter whether I measure your study time in hours or minutes or seconds. The pattern is still the same. The longer you study, the better you do on the exam. So the units of measurement don't have anything to do with correlation. I can change them, and the correlation between the two variables should still be the same. Okay? And then the last thing that's pretty important here, and I'm going to show you an example of this in a little bit, is that correlation is not resistant, right? We talked about resistant measures and non-resistant measures, okay? Mean, standard deviation, range, these are not resistant measures, and correlation is not a resistant measure, meaning if I add a data point that's far away from the rest of my data set, those values will change drastically. And that's a big difference from your resistant measures, things like the median or the interquartile range. Adding an extreme data point won't severely change those statistics for a data set, because it's more about position rather than value. Okay? But correlation is not resistant. If you add an extreme data point, it will change the correlation quite a bit. Okay? And then the last point I want to make on this slide is that correlation does not imply causation. And I gave you guys an example of this in class. Two variables can be highly correlated, but it does not mean that one caused the other. And the example I used in class, right, was crime and ice cream sales. Right? Those are highly correlated variables. On days where there are more ice cream sales, it's been proven that there's also more crime. That does not mean that ice cream causes crime. There's probably something lurking in the background called a confounding variable that's having an effect on both of these variables. And in this case, if you remember, that confounding variable was temperature, right? There's crime. There's more crime on days when it's hotter outside, and there is also more ice cream sales on days when it's hotter outside. Okay, so just because two variables are correlated with one another does not mean that one caused the other to occur. And it's important that we interpret correlation. We don't talk about one variable causing the other to change, right? And you can see, I think they give a good example here, right? Seeing a fire truck every time there's a fire doesn't mean that fire trucks cause fire, right? There's a confounding variable there. Fire trucks show up to put out fires. So every time you see a fire, you're likely to see a fire truck trying to put it out, right? But just because you always see them together doesn't mean that fire trucks cause fire. Okay? So we're cruising on here, right? When you are asked to describe a relationship that you are given in a scatter plot, okay, you need to hit these 4 things. It's kind of like socks when you're describing a one variable data uh, graphical display, right? When you're describing a histogram or a dot plot, you need to talk about shape, center, spread, and any outliers. When you are describing a bivariate data set, you need to first hit on, well, you can hit on them really in any order, that doesn't matter. But you got to hit strength, okay? So the strength of the relationship is measured by the correlation, okay? And they give you a little guide here, all right? This isn't the be all end all, but basically saying that any value between zero point 0.8 and 1 or negative 0.8 and negative 1, those are going to be your strong correlations, right? And if we come back to our correlation slide, here's a 0.8 and here's a negative 0.8. They're going in different directions, but they are strong relationships. The dots are tightly packed. All right. If you have a correlation that's somewhere between 0.5 and 0.8 or negative 0.5 and negative 0.8, you could call that moderate. Okay. And again, that you don't have, I don't think you necessarily have to worry about memorizing that chart to a T, but just remember, right? Like these relationships in the middle here that are 0.5 and negative 0.5, the dots are not as tightly packed together. They're more moderate relationships. Okay. And then if you have relationships where the correlation is near 0, right? So bigger than negative 0.5, but less than 0.5, those are going to be your weak relationships. All right. And again, if I come back to this slide over here, you can see here are your R's of 0.3, negative 0.3. And then I know I've kind of made a mess of this page here, but if I get rid of this, you have your R near 0, 2. You can see the dots are not very tightly packed together. These have very weak linear relationships or very weak correlation, okay? But besides strength, you also have to hit these other things, okay? Direction's pretty easy, right? Are the variables positively associated or are they negatively associated? All right, so that's going to be your direction. All right, and if they have no association, you can say that. But basically, for direction, you're going to want to say, are the dots upward sloping or are they downward sloping? For form, right, that's you're either going to have a linear relationship or you're going to have something that's nonlinear. It is not your job in this class to say, if the pattern is nonlinear, it is not your job to try and say what the pattern is. Okay, so for form, you're either going to say, yeah, these dots look like they could be pretty well modeled by a line, okay? Or you're going to say these dots are a nonlinear pattern. A line is not going to be the best model to model this data. But again, it is not your job to try and say what type of relationship there is. So you're not going to say the relationship, I think it's exponential or parabolic. You're just going to say nonlinear if the pattern doesn't look like a straight line would fit it very well. Okay. And then, of course, the last piece, besides context, you always want to use the variables. You want to talk about whatever is being measured in your response. And then just make sure you make note of any unusual features. If there are any dots that are obvious departures from the pattern, okay, then you're going to want to make note of those. So we can practice this real quick with our first scatter plot here, right? So I would say, to me, I mean, I can understand anybody who was on the fence between saying that this was a moderate to strong relationship. I would say it's pretty strong. I would probably say this is a strong strong, positive, linear relationship, okay, with no unusual features. All right, and I'm not going to write all that out because I'm pretty slow with the mouse. But like I said, I can see upward sloping lines. They're pretty tightly packed together, so I'm saying strong, positive. A line looks like a pretty good choice to model this pattern, and I don't really see any dots that are really departures from the pattern. And then I would throw some context in at the end, right? I would say this scatter plot, the best way to describe this scatter plot would be a strong, positive, linear relationship between number of hours studied and score on the test. And there are no unusual features on this scatter plot. Okay? So that's just describing a scatter plot if you're asked to do that. Okay? Next, you have to be able to interpret regression data. So in a separate video, probably, I'm not going to go through all these slides in this video. All right, I'm going to do some practice problems later. But you need to be able to interpret regression data that's given to you. This image at the top, all right, is computer generated regression data. And this image down here is calculator generated regression data. All right, I need you to be able to read them both. They both are giving the same information right now. So when it comes to the printout, all right, you're going to see this image on the exam for sure. They love to ask questions based on this box here. A lot of these numbers are given to you for what comes in the very last chapter, which we did not cover and is not very heavily represented on the exam. So for now, let's just say that you don't really need to look at these numbers over here. What's important for you guys is to know R squared and to know how to determine what's going on in here. All right. So again, it looks like we're still trying to predict somebody's score on an exam based on the number of hours they spent studying. And I can convert this into, a little bit more algebraic. I can say y hat. Remember, we always put a hat when we're dealing with correlation, right? Because these are predicted values. There's no law that says if you study for X amount of hours, you have to get a certain score on the exam. It's just our best prediction. So y hat is going to equal 59. That looks like the y-intercept plus 6.77x. All right. And there is your linear regression equation. That's pretty ugly. Let's see if I can just do better than that real quick, right? 59 plus 6.767x. And this equation will give you a prediction on somebody's score on the exam based on any number of hours. Now, on the exam, they're not going to give you the equation here. You would have to build this on your own. So you have to know that look under the coefficient column, and that's going to give you the numbers that you need to make the equation. The constant is just, your y-intercept out here. And then the coefficient that they give you for the variable is going to be the slope of the linear regression line. And you need to know how to interpret these numbers as well, right? So if I wanted you to interpret the y-intercept, you would say something like, somebody who didn't study at all would be expected to get a score of 59 on the exam, right? Because if I spent 0 hours studying, if I substituted in a 0 here, 0 times 6.767 is still 0. So the predicted score of somebody who didn't study for any hours would be a 59. They also might ask you to interpret the slope. So think, what's going to happen to my predicted score for every 1 additional hour spent studying? Well, the equation tells you that every time I increase x by 1, my predicted score should go up by 6.767 points. And that's how you would interpret the slope, right? Every 1 hour increase in time spent studying leads to a predicted score increase of 6.767 points. Be sure to use the word predicted, okay? There's no law in nature that says every time you study an extra hour, you're guaranteed to get an extra 6.7 points on the exam. All right. It's just a prediction. Alrighty. Now, the calculator output gives you the values of r squared and r. We're going to talk about how to interpret r squared in a little bit. But just in case you're not given the calculator output, you're given the computer output here. And you're asked to determine what r is based on r squared. R squared and r have a very obvious relationship between each other. It is not a trick question, right? R squared really is this number r to the second power. So if they give you an r squared of 74.7, or I got to turn that into a decimal if I want to work with it, 0.747. If this is my r squared and I want r, well, if I have r squared, the square root of r squared is equal to r, right? So if I want to define the correlation coefficient, or r, I would have to take the square root of this number, all right? So I can pull up my calculator here and take the square root of 0.747, and it gives me 0.8682, and we're slightly off, right? But it's still the 0.86 because I didn't take the square root of this whole r squared number, right? They rounded it off in the computer output. So I took the square root of 0.747. In reality, it looks like it's 0.74703131175. I truncated the decimal, which is why they don't match exactly on my calculator, but you can see the relationship anyway. If you take the square root of r squared, you're going to get the correlation. And this correlation of 0.86 tells me that there's a pretty strong positive linear relationship between the number of hours studied and the score on the exam. All right. So here are a couple extra formulas that you don't need to memorize. All right. These formulas are right out of this chapter of the 5 steps to a 5. Okay, here is the equation for the least squares regression line. It's the same thing that we saw on the previous page. Y hat, some predicted value, is equal to A, which is the y-intercept, plus B, which is the slope, times X, which is the explanatory variable. Okay, so this shouldn't be shocking to anybody. This formula right here is for the slope of the least squares regression line. Okay, you can see B, the coefficient that's attached to the x variable. When you're thinking about a line from algebra, right, this is the slope of the line. And they give us the formula for the slope of the line. It's equal to the correlation times the standard deviation in the y variable divided by the standard deviation of the x variable. And then they also give us the formula for the y-intercept of the least squares regression line, and that's equal to the average of all the y coordinates minus the correlation times the average of all the x coordinates. You do not need to memorize these formulas. This is a copy of one section of the formula sheet, okay, from the exam. Here is the formula for the least squares regression line. Here is the formula for the slope of the least squares regression line. Right, there's B. And here is the formula. They have it a little bit out of order, right? I would like it better if this was solved for A, right? The y-intercept for the least squares regression line is equal to y bar, or the average of the y values, minus the slope of the regression line times the average of the x values. All right. And, you know, I'm not going to go too much in detail of explaining why this formula is the way it is, because they're giving you the formula sheet. You're not going to need to derive this formula. And on the next slide, I'm going to give you an example of when you would need to use this. Okay. Is it the next slide, or did I save that to the end? Nope. We're going to do it right here. Okay. We're going to do 2 examples of when you would need to apply these formulas, but this is where they are. Here's the formula for correlation itself, which you are probably not going to have to use. This is the standard deviation formula. You don't need to worry about that right now. This is the formula for a mean, right? So you don't need this right now. These are your least squared regression line formulas that you need to know, and they are all on your formula sheet. All right, so let's look at an example. It says, given a two variable data set such that the average of the x values is 14.5, the average of the y values is 20, the standard deviation of the x variables is 4, the standard deviation of the y variables is 11, and the correlation coefficient is 0.8, find the equation for the least squares regression line. If we got this question on the exam, we should be happy because we have all the formulas to solve this, right? We know that y hat is going to be equal to some y-intercept plus the slope of the regression line times the explanatory variable. Okay, and if I go back a slide, if I want to find the slope of the regression line, I'm going to take the correlation and I'm going to multiply it by the standard deviation in the y variable divided by the standard deviation in the x variable. And they give those to us in the question. The standard deviation for the y variable is 11 divided by the standard deviation for the x variable is 4. Okay, and they tell us that the correlation is 0.8. 0.8. So the first thing I'm going to do is calculate the slope. I'm going to do 11 over 4. 11 over 4 times 0.8. And there's my slope, okay? The slope of the regression line is going to be 2.2. 2.2. Now I just need to figure out the y-intercept, all right? So again, I'll come back to my formula, right? The y-intercept is going to be equal to the y-average minus the slope times the x-average. So here you go. The y-intercept is going to be equal to y-bar, which was 20, minus the slope, which we just calculated, which was 2.2, times the average of the x's in this case, which was 14.5. 14.5. So I'm just going to plug this equation into my calculator. 20 minus 2.2 times 14.5. 20 minus 2.2 times 14.5. And I get that the y-intercept is going to be a negative 11.9. So there is your equation, right? Y hat is going to equal negative 11.9 plus 2.2x. They don't even need to tell us what we're actually measuring here. If you just know how to use these formulas, you can work these out here, right? And then this one underneath too, right? It says given the set of ordered pairs where the standard deviation of the x variable is 1.6, the standard deviation of the y variable is 0.75, and the correlation coefficient is 0.55, what is the slope? We're going to use that same formula that we used before, right? We're going to use B is equal to R times the standard deviation in X divided by the standard deviation in Y. All right, the correlation here is 0.55. And the ratio there is 0.75 over 1.6. And just plug this into your calculator. All right, 0.75 divided by 1.6, and I got to multiply that by, what was it, 0.55, I believe was the correlation coefficient. Whoops, 0.55, I want to multiply. I didn't do that in my calculator, right? I want to multiply by this number here, and we get 0.2578. Is that an answer choice? Yeah, 0.26, right? 0.2578 rounds off to 0.26, right? So you just got to know that these are going to be right at the top. They're section 1 of the formula sheet. And if you can understand these three formulas, you can answer most of the multiple choice questions. A couple more things, and then I'm going to cut this video off and I'll make a separate video where I do more practice questions. But I was talking about earlier how the the correlation coefficient, is not resistant. Okay, check out these two graphs. They're almost exactly the same. If you look at this one on the left, and I'll change my color here, this is a downward sloping pattern. Okay, and that's clear based on the correlation coefficient of negative 0.8. But if I add one extreme data value that does not fit the rest of the pattern, okay, the least squares regression line is no longer downward sloping. Now, the best way to model this pattern would be to do this, okay? So you can see that the correlation changed to 0.51 when I added this one extreme data point. Right? So that's why the correlation coefficient is not a resistant measure. Adding this one data point over here drastically changed my value for R. All right. A couple more things we have to touch on. One is the idea of a residual. Okay. The residual, when you are calculating a residual, it's an actual data point value minus what my regression line predicted, right? So actual data points are represented by Y, right? And the prediction of our regression line is represented by Y hat. So if you ever wanted to calculate the residual, you got to be thinking, all right, what was the actual data value minus what did my regression line predict? Okay? And you can see here, the residual is the distance, the Y distance, or the vertical distance between the data point and the regression line. So here, you have a positive residual, okay? The actual value, the actual Y value of this data point is above what my regression line predicted, right? So Y, the actual value, minus the predicted value is going to give me a positive number, because this is above the line, all right? And the opposite can be said. If a dot falls below the line, it's going to have a negative residual, right? The actual data point minus what I predicted is going to give me a negative number, because my regression line predicted the Y value over here was going to be much higher than what it actually came in as, okay? So the actual value minus the predicted value gives you a residual. If a dot falls below the line, you're going to get a negative residual because the actual value is lower than the prediction. If your dot falls above the line, you're going to get a positive residual because the actual value is greater than the predicted value. Okay? And then a couple more things to squeeze in here at the end. We talked about residual plots. Okay? A residual plot can give you an idea of whether or not a linear model is appropriate for the data. And essentially what you're looking for in the residual plot is a pattern. If you can't see any pattern in the residuals, it means the line of best fit was a good model for the data, and the data is probably linear, okay? So here's a scatter plot on people's ages versus their heights. And as you can see, this linear model splits this data down the center pretty well. And if I look at this residual plot, I can't really pick up a pattern here, right? This data point right here fell above the line. That's got to be this data point right here, right? This is the distance between this data point and the line, okay? Same thing, this data point right here has got to be this guy. This data point over here had a negative residual. That's got to be this guy. I don't really see a pattern here, though. It kind of just looks like random scatter. And that tells me that this line is a good fit for this data. Whereas this is another regression line for data that's clearly not linear, right? You can see that the line does not fit this pattern very well. I got a clear curved pattern here. And you can tell by looking at the residual plot that this did not fit very well, right? Look at the first two residuals. They both fell above the line, okay? Or the first two data points. And if you look at their residuals, right, the residual plot is always centered around 0. So these had positive residuals. Then the next 1, 2, 3, 4, 5 data points all fell below my regression model, meaning they have negative residuals. 1, 2, 3, 4, 5 data points over here are all having or are all below 0. They all have negative residuals. And then the last 2 data points fell above the regression line, and you can see over here the last 2 data points have positive residuals. There's a clear curved pattern in my residual plot, and that tells me that a linear model was not the best model for this data, right? It's kind of intuitive if you look at it, right? The line does not fit this curved pattern very well. When I look at the residual plot, I don't see random scatter. I can see that certain areas of the graph had a lot of dots fall above the line. Certain areas of the graph had a lot of dots fall below the line. We didn't do a very good job of splitting this thing down the middle, and therefore a line is probably not the best way to model this pattern. All right. And then the last topic, okay, is how to interpret R squared. First of all, this is something you guys would probably need to be able to do on the exam, right? They're trying to predict weight based on height, right? So to plug in the numbers here, right? The coefficient for the height, they tell you right here, is 3.4715, right? And then the y-intercept is negative 104.75. I'm not going to put the 0.75 right now, right? But that would allow you to create the regression equation based off the computer output. And what we need to know about R squared is that it tells us the proportion of variability in Y that can be explained by variation in X, basically. That's what you're going to say on the exam. If you are asked to interpret R squared, you don't have to worry about adjusted R squared. It'll be on the computer output, but you don't need to worry about it. If you are asked to interpret R squared, you are going to say, can I type this? Yeah, let's type R squared, or the otherwise known, how do I type in here? I don't want my font to be enormous. Okay. I would say here that 84.8% of variation in height can be explained by, or sorry, I have this wrong. I have it backwards, right? I should have put weight here. 84.8% of the variation in weight can be explained by variation in height. That's what R squared tells you. All right. It tells you how good my explanatory variable is at explaining measures in my response variable. So if you have an R squared of 84.8, that tells you about 84.8% of the variations in people's weight can be explained by variations in their height. The remaining, 15-ish percent is going to be explained by other factors. Okay. So according to this linear model, the majority of your weight can be explained by your height, and the rest of it must be explained by something else. Okay. And that's R squared. Okay. You just need to know that R squared tells you how good the model is, how good is your explanatory variable at explaining the response variable. Okay. And just to repeat it one more time, like I said, this is telling you that 84.8% of variation in people's weight can be explained by their height. The rest of it must be explained by something else. And just really quickly, and then I'm going to end this video and I'm going to do some practice questions in a separate video. All right. If you were asked to find R here, because they don't give you R, just take the square root of R squared, right? You got to turn it into a decimal. So 0.848. If I take the square root, it's going to give me R. So if I take the square root, 0.848, There's my correlation coefficient of 0.92. Okay, so I'm going to end this here at 50 minutes, and I'm going to do some practice questions on these next slides for you guys, and that one should go relatively quickly. All right.